All right, thank you all for coming. Last talk, I wasn't expecting this many people to show up. So this is kind of the abstract of the study. Basically, deep learning currently has a bloom of frameworks and backends, frameworks to use, popular data sets that are getting used, and stuff like that. So kind of the purpose of this talk was to kind of run through some of the various frameworks and which ones specifically interact with Spark, and then also kind of provide a case study that we put together at BitFusion. So kind of going into the landscape, right? So there's kind of the base frameworks that popped up, which are like the TensorFlow, MXNet, Caffe, Torch, Theano. Since I wrote this, a lot of PyTorch and Caffe 2 stuff have been popping up out of Facebook. And some of the more boutique frameworks like TensorFlow and Spark, Caffe and Spark. Some of the data backends, just a EFS, just regular file systems, Spark, Hadoop, et cetera. And then where you can run all these deep learning models, right? Because most of them get huge performance gains from GPUs, so you need to find the GPUs. And they mostly exist, in AWS or cloud instances or on your own hardware. So why you do use Spark? This is just kind of a slide to kind of go over what are the kind of benefits of using Spark for a lot of the deep learning tasks. And a lot of it has to deal with the reading and memory and placing the data onto the GPUs. So approaches to deep learning in Spark. So there's the Caffe on Spark and TensorFlow on Spark. Some important things that I'm going to kind of highlight later on are this gRPC versus RDMA. It ends up being kind of a key differentiator on deep learning frameworks when it comes to going to distributed settings or going across multiple GPUs. So also Skymind AI has deep learning 4J, which also it sits on top of Spark or Hadoop, and it's another framework. SystemML, yet another framework that kind of sits on top of Spark, and it's a deep learning framework. Until BigDL, they literally just went over this one, so I'm going to skip that one. And then kind of my personal favorite and the most popular is Google TensorFlow. I kind of actually took this from their roadmap, but as far as I know right now, this is version 1.1, version 1.2, and then this is going to be expanded in version 1.3. But as of now, there's Keras support and TensorFlow. So obviously, I just said I use TensorFlow a lot. So why do I use TensorFlow? Well, this kind of gives you an idea of the web popularity of the different deep learning frameworks. So we kind of want to make this talk as ubiquitous for people as possible. So most likely, if you're doing deep learning, you're using TensorFlow or Keras. And this kind of shows, research over time, research papers getting submitted over time to kind of give you the idea that TensorFlow is not really going away anytime soon. So now I'm going to kind of get into, I guess, what I did, which is the quick case study that I kind of want to go through. And I wanted to walk through things a little bit differently, because when you get to scaling or performant deep learning models, you see a lot of 64 GPU configurations, 8, 16, so on and so forth, like tons of GPUs being used. But sometimes that doesn't really tell the full story. And what I mean by that is it's really easy for the frameworks to take that batch size and really pump it up such that the number of communications between servers goes down a lot. And that way they're able to easily illustrate linear scaling, when in reality, what I care about as a data scientist is the time it takes for me to get to a certain threshold at accuracy. So I'll kind of go over that in the next few slides. For you guys to kind of look at what I used, what I did, this is the model. So I used the CFAR10 data set, not a huge data set, just a step above that MNIST data set. The architecture is obviously pictured to the right, where I have the 2x2 convolutional, the two convolutional module which is a 3x3 and a 3x3, followed by a 2x2 max pooling layer with a stride of 2. And then you can see the depth kind of here in each layer of what I used. And so this is basically a play off of VGG. Nothing super novel. It was just kind of to illustrate the different configurations and how you can get performance off of various things. So for benchmarking, we're going to consider images per second, something that we see a lot. We're also going to look at time to 85% accuracy, which I kind of just discussed. I averaged this run across 10 runs to kind of get a distribution. And then one thing to note is I ran this on as homogeneous of hardware as I could. So I just used P2 AWS instances, and that's all I used. And I'll kind of get into further optimizations for specific frameworks later on in the talk. So again, the configurations that we're going to talk about are going to be the single server with a CPU, single server with a GPU, single server multi-GPU, multi-server distributed TensorFlow, and then multi-server TensorFlow on Spark. So here's basically the single server CPU and GPU. Excuse me, I have a little bit of a cough. What you'll see is basically I'm going to summarize the performance up here, and then I'm going to kind of give some bullet points. And basically, this has been very well documented since the days of Hinton when he had his breakthrough paper, that GPUs are really good when you're trying to do deep learning. And you can kind of see the performance game. And I'm also going to give a kind of a bar chart that summarizes all these together at the end, if you guys are going to wait for that. But this is obviously the 10 runs. The reason you kind of see a step function is I only updated the test accuracy every 5 epochs, I believe. So that's kind of why you see a step function here. So then for the single server multi-GPU, what you can see is pretty much doubling the speed when going from 1 to 3 GPUs. I also wanted to do kind of a GPU configuration that you usually don't see in the benchmarks, 3. So a few notes on multi-GPU TensorFlow. You have to recode your code base such that you're averaging your gradients across each GPU as you place your data across those. So I kind of gave some blurbs on things like the big hurdles of where you kind of need to recode things. So then in distributed TensorFlow, so for this one I used 1 parameter server, 3 worker servers. I just used EFS on this one, so share file system across those P2 instances. And then kind of in general sense, when you want to write distributed TensorFlow code, some of the key things that you need to look for are the TF monitored session, which kind of, you can configure it to run synchronous or asynchronous for your distributed running. And then you needed, for a lot of these examples, you need to balance batch size and learning rate to optimize throughput. So this is kind of what I was getting at the beginning of this, is the number of communications that have to take place between each worker and the parameter server goes up a lot if you have a small batch size, right? So there's a lot more communications happening over network, which ends up really taking that performance number that you see up there. So if you actually look at it, you don't see a whole lot of performance increase when you go to distributed TensorFlow in this example, using AWS hardware and just P2 instances. And then the last one was TensorFlow and Spark, which we did end up seeing more speed up. I'm going to talk about one thing where I think TensorFlow and Spark will really shine. It's something that I didn't do for this study, but it's something that we at Bitfusion put in our product, and it's something that will really scale this performance really well, and that's their use of RDMA instead of gRPC. But for this one, I don't think the right RDMA over InfiniBand stuff was configured on the AWS instance. So this is kind of the performance that I got. And my theory on why it still got better is just Spark's ability to have fast access to data in memory. So here, again, is kind of that bar chart that I was going to give you, where you kind of get an idea of how they stack up next to each other. So obviously, higher is the better. All right, so kind of getting into what I was alluding for a long time is when to use what, right? So number of updates means a lot when you're going to a distributed framework and you're using deep learning. So number of updates gets balanced between number of updates getting communicated across servers and number of updates getting computed basically on the GPU, right? So really, really large models end up taking a lot of bandwidth on the GPU, in which case some of the performance over network gets phased out. What I used was CFAR10, not phased out, but it gets mitigated. So what I used was CFAR10, right? So as soon as that data gets placed on the GPU, it got consumed almost immediately. So a lot of the bottleneck in that case is the network communication that's happening from model to model. So obviously for the multi-GPU, all of that was taking place on a single server, so it ended up going a lot faster than the parameter server that had to communicate over network. And then so to kind of give you guys an idea of what we've seen in some of our other studies is GPUs connected with RDMA over InfiniBand have shown like significant speedups over gRPC over Ethernet, which is basically what you're using when you're using the basic P2 instance on AWS. And this is kind of what we saw as far as scale up versus TCP, which is close in performance to gRPC. So we got 2 times faster with 2 nodes and 10 times faster for 4 nodes. So then what we essentially get into now when you go to a distributed setting is what distributed framework is, what communication primitive over the network is fastest for the network that you're using, right? So this is pretty rich text, but basically what we've seen is RDMA over InfiniBand gives the best performance. One of the things that we're very interested in looking at is Tensorflow just released an MPI-based distributed version in their contrib. So we're very curious in seeing how that performance might stack up against what we've seen over here, and also RDMA over InfiniBand. So my point in saying the RDMA over InfiniBand is TensorFlow and Spark is configured out of the box to run that in that sense. I just wanted to illustrate stuff on commodity hardware, or what you might use if you're just starting out of the box in the cloud. So some other practical considerations would be the size of the model, kind of what I was getting into, where you put the burden of compute on GPU versus on the communications, and then the size of the data. So some of the key takeaways: GPUs are almost always better. The hardware and network setup matters a lot when you go to a distributed setting. And then saturating GPUs locally should be a priority before going into any distributed setting. If your data is already built on Spark, TensorFlow and Spark provides an easy way to integrate with your current data stack and also provide what we've seen to be the fastest communication primitive. Again, it's natively supported by TensorFlow and Spark. And so we actually have a proof of concept with Dell using their InfiniBand cluster. And then just to kind of give you an idea of what BitFusion does. So we basically do these studies all the time. And what we do is we bake what the best communication primitive is into a GPU virtualization software. So we're able to virtualize GPUs in such a way that you might be able to split a single GPU into 4 or 5 GPUs, or you might be able to let one server see GPUs that are on another server. And that's why we care so much about these communication primitives and why RDMA over InfiniBand is so important to us, is that's what we've seen to be the fastest when we just want to scale a model from 1 GPU to 64 GPUs. And again, what BitFusion provides you is the ability for any one server to see all 64 GPUs across your cluster. So obviously, for more information, you can go to our website. This is a demo of our Flex platform, which is a web-based interface to our software and your server stacks. And that's it. Any questions?
Yeah, about the comparison you did between CPU and the GPU.
Yep.
And the gap it shows like more than 100 difference. So the TensorFlow you got is from, does that use Intel's MKL?
Sorry, what was it?
I mean, so I guess there's a TensorFlow workload you use, right? TensorFlow engine. And I just wonder, the TensorFlow on CPU performance is so low, so it's not fair to Intel platform. You know, I wonder whether this TensorFlow you are using use Intel's MKL or not.
So I used the commodity hardware that I kind of presented, right? I wanted to make all the hardware homogeneous when I did the study. And I think for some models, those kind of level out, but for mine, it didn't.
No, not the hardware, the software stack, the TensorFlow. I think it should configure to use Intel MKL.
Oh, okay.
Yeah.
I'm not sure if I did.
Okay, yeah. So yeah, that's my point. I work for Intel, so the comparison is just GPU is faster, but not 100 faster, you know. So guys, use MKL.
So one of the questions I had about those benchmarks you did is, I'm guessing in a lot of cases you were starving the GPU. Was that the point, or did you check to see if that was happening, or because it's a relatively small model and I think those instances have P100 GPUs, right?
Sorry, what was the question?
So I'm wondering if you checked to see if you were like feeding the GPU data fast enough in those things, or was that the point?
Yeah, so the GPU saturation was reaching 90% pretty
Okay.
consistently.
Okay, thank you.
And it really depended on the configuration, right? Because if the communications were taking place on the distributed setting, and it took a while for basically the parameter sharing to come back to the workers, obviously I wasn't hitting saturation at that point. But when I was doing the multiple 3 GPU configuration, I was getting full saturation from the NVIDIA SMI.
Okay, thanks.
Yes, the result that you showed for distributed TensorFlow is a little disturbing because you showed no improvement at all, right? I think we're still going 1500 to 1400.
Right. So that's kind of what I was getting at with the networking. Networking plays a huge role when you're going to distributed TensorFlow, right?
Okay. But I did see some results of even on Cypher 10 where distributed TensorFlow showed improvement. We had some other tests where it showed improvement. Not linear and maybe a little depressing compared to other database or analytics algorithm that's semi-linear, but to show no improvement, is that something I was missing in the optimization there? Maybe playing with the batch size or something that could show?
So one of the things that I really wanted to focus on was not arbitrarily increasing the batch size to increase the number of images processed, right? My goal was to basically get something that got the fastest 85% accuracy possible, right? So I was more performant on getting a thresholded accuracy than I was at boosting that images per second number.
I see.
So that was very important for me as part of this study.
Anyone else? Okay, I guess that's it. Thank you for your attendance.